In this lecture, we will discuss about the self-induction. Self-induction is a phenomenon in which a rate of change of electric current in a coil or in a conductor induced an electromotive force in it. So we can write the definition of self-induction as self-induction is a process in which the rate of change of current in a coil or conductor induces electromotive force in it. So dear student, whenever there is a change in a current in a coil, then with the change in a current there will be a production of an electromotive force. Since you know that every wire or any kind of coil, if it has a current, then in the current also have an associated magnetic field of line with it, and the magnetic field of line basically have a flux, and that flux is known as magnetic flux. Magnetic flux basically represent a number of magnetic field of line passing through the surface. So in such situation, when the magnetic field of lines, when the current in a wire or a coil is constant, then there will be a constant magnetic field, and the flux in a coil or a wire will be also constant. This means that there is no change in flux, so electromotive force in such type of coils will be zero. However, in some cases, if there is a change in a current, and the change in current will cause a change in magnetic field, and change in magnetic field result into change in a magnetic flux, and whenever there is a continuous change in magnetic flux, then there will be a generation of electromotive force, and whenever there is electromotive force in a wire or coil, then there will be an induced current inside the wire. So now, if we in self-induction, there is only one coil which is connected with a potential source, and when there is a voltage is applied in the coil, and if the current of the coil continuously changes, then the change in a current basically will cause an induction of a current, or it will cause a production of induced EMF. So this means that induced EMF in self-induction, induced EMF is directly proportional to rate of change of current. Greater will be the rate of change of current, greater will be induced EMF. So now we can write this equation as induced EMF is equal to constant into rate of change of current. The constant for self-induction is represented by L, and it is called self-inductance. So we can write this equation as induced EMF is equal to L into rate of change of current. Now, dear student, please note that according to Lenz Law, induced EMF is always opposite to the source, which is basically causing the production of induced EMF. So due to this, negative sign will be used in this equation. So we can say that induced EMF is equal to minus L into rate of change of current. So Whenever there is a change of a current in a coil, there will be a production of self-induction in a coil in a form of production of an induced EMF. Now, the unit of self-induction else we can find it by equation from the equation of self-inductions. So if we consider the equation of self-induction, L self-inductance will be equal to EMF into rate of change of time divided by current. So as we know that the unit of EMF is volt, the unit of current is second, and unit of time is second, and unit of current is ampere. So the unit of induced EMF, self-induction, sorry, unit of self-induction L will become volt second per ampere, and it is also known as Henry. Dear student, please keep in mind that 1 Henry is equal to when there is a 1 volt applied in a coil and it induces a current of 1 ampere in 1 second. So whenever there is an application of 1 volt in a coil, it's produce a current of 1 ampere in 1 second, then it will be called that we have a self inductance of 1 Henry. So now let us just represent self induction with a schematic diagram and then explain the phenomenon of self induction schematic diagram. Just suppose that we have a conducting coil. This is schematic diagram of conducting coil. And this coil is connected with a voltage source. Suppose this is a battery. Let me redraw the image of battery. This is a wire and it is connected with a battery like this. You know that we have a positive terminal and negative terminal present in a battery, and one side of this wire is connected with an electronic component known as rheostat. Rheostat. The role of rheostat is very important in self-induction process. Rheostat basically changes the resistance in a wire. Whenever there is a change in a resistance, there will be a change in a current. And change in a current will cause basically change in a magnetic field. So in this circuit, whenever the voltage is applied on coil, there will be a generation of an electric current, and there will be a flow of electric current, and this electric current, if this electric current is anti-clockwise, if it is like this in a coil, then there will be basically a generation of a magnetic field B. Student, please keep in mind that when a current flow through a coil is anti-clockwise, then one side, the right side of the coil, act as a north pole, whereas the left side of coil act as a south pole. And as you know that in magnet, The magnetic field of line, basically in magnet there are two types of pole. One pole is known as north pole and other pole of magnet is known as south pole. And in magnet, the magnetic field of lines are generated from north pole and they travel toward the south pole like this. Whereas the magnetic field of line come toward the south pole like this. So now, since the current in a coil is anti-clockwise, then the right side of the coil act as a north pole, whereas the left side act as a south pole. So this means that electric field of line will be magnetic field of line will be generated in this coil like this. So now, dear student, please keep in mind that if the magnetic field, if the current in a coil is continuous or it is uniform, then the current is moving but it is uniform, then it will basically generate a constant magnetic field of line and the field will be also constant. And since the number of magnetic field of line passing through an area is known as flux, then within a constant current the magnetic flux will also be constant. When magnetic flux is constant, then there is basically no change in a magnetic flux in in a specific amount of time. This means that the current induced EMF in a coil is basically induced when there is a change of flux. So when the current is constant, then induced EMF will be zero. However, in this system, as you know that we have used rheostat basically change the resistance. Rheostat basically changes the resistance, and when the resistance changes there will be a change in a current, and whenever there is a change in a current in a coil there will be a change in magnetic field of lines, and whenever there is a change in magnetic field of line there will be a change in magnetic flux, and the change of magnetic flux will basically result into a change in a magnetic flux in a unit time, basically will result into a production, into a generation of an electromotive force. And whenever there is an electromotive force in a circuit, then there will be a production of an induced current. So basically we can write that in induced EMF, in self-induction, the induced EMF is basically directly proportional to the rate of change of a current in a circuit. Whenever there is a rate of a change of current in a circuit, there in a coil, then there will be, if if is we are using single coil, and if there is a rate of a change of current in that coil, then there will be a production of induced EMF in that coil, and that induced the process in which an induced EMF is produced in a single coil is known as self-inductance. Dear student, please keep in mind that self-induction also depends on the number of turns of coils. Greater will be the number of turns of coil, greater will be the induced EMF produced in a circuit. So this is all about self-induction. Self-induction is a process in which a rate of change of current in a coil produce an electromotive force in it. So this means that whenever there is a constant current in a coil, there will be a magnetic field of line, but the flux of those magnetic field of lines are not changing in a constant current, so there will be no EMF. However, if there is a change in a current, and then the change of current will basically lead to change in a magnetic field and a magnetic flux, and the change of magnetic flux will basically produce an induced EMF in a wire, and such induced EMF of in a single wire or coil is basically known as self-induction. The unit of self-inductance induction uh, is in self-inductance, and it is equal to Henry, or the unit of self-inductance is known as Henry. So this is all about self-inductance. Thank you for watching this.